Alright, so today we're looking at energy and phase changes. So this is related a little bit to what we talked about last time with specific heat. So today we're looking at a concept called latent heat, and we're going to look at some energy diagrams to help us explain what's happening to the energy in a chemical reaction or when we're going through phase changes. Now keep in mind that for these notes we're looking at phase changes. So a phase change is when anytime we go from a solid to a liquid to a gas, or from a gas to a liquid to a solid. So if we were to draw a phase change diagram, then we have temperature over here. So there's our temperature, our reaction is going this way, and as we raise the temperature, okay, then what happens is it starts to level off. And so here this would be something like a solid, like ice. Then the temperature stops changing and then it starts increasing again. So while we're here, this is a liquid, and then all of a sudden it starts boiling, and finally once it's all boiled, then it starts rising again, and that gives us a gas. So remember, this right here is a phase change, this right here is a phase change. For this one, if we're going from a solid to a liquid, remember that is melting. Okay, and if we're going from a liquid to a solid, that is freezing. Then over here, if we're going from a liquid to a gas, that is boiling or vaporization. And if we go in this direction from a gas to a liquid, that would be condensation. Now, last class, remember we talked about specific heat, and anytime we have specific heat, it's when the temperature is changing. So we can see specific heat happening here, or we could use a specific heat equation here, here, and here. So remember, when we're dealing with specific heat, we use the equation Q equals Cm delta T. Now, that worked out just fine when we were dealing with the change in temperature, but what we're going to see today is that when we're looking at an actual phase change right here and right here, we can't use that equation because there's no change in temperature, so this variable right here would always be 0, meaning that our heat would always be 0. So in order to determine the heat that is released either here, or the heat that's gained in those two spots, then we have to use an entirely different equation, and we'll get to those equations in just a little bit. Now, I'm going to show you guys something a little bit that's going to help us to determine the difference between endothermic and exothermic in terms of phase changes. Now, this is also something that you can, once you've done on your notes, you could also add these to your interactive notebooks, and it's on page 74 and 75 for endothermic and exothermic. So basically what we want to do is look at the phase changes and see whether it's going to be an endothermic process or an exothermic process. For the first one, if we go from a solid to a liquid to a gas, let's think about what's happening in terms of energy. In a solid, the molecules are tightly packed together, okay, in an orderly fashion. Now to go to a liquid, the molecules are still fairly close together, but they're more fluid, okay, and they're a little bit more spread out, not too much more spread out. And then in a gas, they're very far apart. So if we're going in this direction from a solid to a liquid to a gas, or even skipping the liquid phase and going straight from a solid to a gas, then it's going to take energy in to get those molecules to move around. Because remember, these molecules are moving around a lot more, so they have a high kinetic energy, whereas these molecules are just barely moving. They might be vibrating, but they're barely moving, so they're not moving around nearly as much as in a gas. So to get those molecules to move around a lot more over here, we have to constantly, or we have to supply energy to whatever it is. If we're looking at water, we have to give it energy. In other words, we have to heat it up. So if we are heating up the system, then that means that this system is taking in energy. So if we start with something like ice over here, it's taking in energy, and so then the molecules spread out, they get a little further. If we keep adding energy, the liquid water takes in more energy, and then it becomes a gas. So because the solid, so going from a solid to a liquid to a gas is taking in energy, this would be an endothermic process. Okay, and remember with endothermic processes, that means that the delta H is a positive value. Now, we're going to do the same thing, except this time we're going to start with a gas, go to a liquid, and then go to a solid. So again, I want to draw the dots. We have our dots spread out here. Liquid, they're a little closer together. And then solid, they're nice, neat, and orderly. So if we have a gas, those molecules have a lot of energy. They're moving around a lot, so they have a lot of kinetic energy. So if we want to go to a liquid, then we are going to need to remove heat from those molecules, remove energy from those molecules. If we want to remove energy from those molecules, that means that these molecules are going to be giving off heat. So to go from this stage to this stage, those molecules must lose heat. So if heat is exiting these molecules, then we say that is an exothermic process. So this direction is exothermic. And remember, anytime it's exothermic, that tells us that the delta H, or the enthalpy, is equal to, or is a negative value. So that's the difference between endothermic and exothermic. If we put this all together on one diagram, remember a solid and a liquid can go back and forth, liquid and a gas can go back and forth. So we know that we can go back and forth. If we go in this direction, then to go from a solid to a liquid to a gas, it has to take in energy. And if it is taking in energy, that means it is an endothermic process. Okay? Now to go in the opposite direction, to go in this direction, we would have to give off energy. So to give off energy, that means that it is an exothermic process. Okay? We also know that endothermic, the delta H is positive. And for exothermic, the delta H equals a negative. We could also say that heat is a reactant for endothermic. Heat is a reactant. And we can say for exothermic that heat is a product. Alright, now here's your first question. Question number 1. Why can't the equation Q equals Cm delta T be used during the phase changes? So I want you to take 10 seconds when I say go. Think about this question. So this is your think time. So go. Now, turn to your partner. I want you guys to discuss this answer, and then I will call on somebody at random to answer it for me. Okay, good. Now here's question number 2. How are endothermic and exothermic processes related to phase changes? So I'll say the question again. How are endothermic and exothermic processes related to phase changes? So you should talk anything about the enthalpy, the direction that the phase change is happening, however you want to discuss it. Just make sure you're covering how those two processes are related to phase changes. Hey, go ahead, take 10 seconds to think about it. And now share with your group. Okay, now we're going to look at something called latent heat or latent heat, okay, depending on how you pronounce it. For latent heat, you are adding energy to a chemical or to a system, and because it's producing a phase change, there's actually no change in temperature. So if we draw an energy diagram, a phase diagram again, so here's our phases. Now what happens, remember we have a solid, we have a liquid, and then we have the gas up here. When we are going from here to here, the temperature is increasing. But our focus today is here and here. These are where we actually have our phase changes during those 2 points. Those are the phase changes. Now, notice that when the phase is changing, so going from, for instance, the solid to a liquid right here, heat is still being added to the system. So if we said that we're adding heat, so this is how much heat we've added. As we add heat to the system, at first, in this portion, the heat is being added to raise the temperature. So it might be freezing down at this end, and then once you get here, that's where it starts to melt. So during this portion, the temperature is changing. But when we get from here to here, we keep adding heat, but there's no change in temperature. Same thing here. From here to here, we keep adding heat, but there's no change in temperature. So remember, during a phase change, there's an energy change, and this is happening with potential energy. So during a phase change, we're actually changing the potential energy within the system. So if we're going from a solid to a liquid, we're increasing the potential energy. If we're going from a liquid to a gas, we're increasing the potential energy. And that potential energy is being used to break those bonds, to spread them out, to give them more energy. Now, it's only once that we've reached this point and all the solid has been converted to liquid that the temperature begins to change again. Same thing happens over here. Once we go from here to here, the temperature is not changing, it's staying the same. But once all of that liquid has been converted to a gas, then the temperature starts going up again. And so this is what we mean by latent heat. And the term here for latent, we say hidden, because even though we're adding heat to it, it doesn't look like we're really doing much, because all that heat is going to change the potential energy, but we can't observe it directly because there's no temperature change at that point. Alright, so this is where we get to our next set of equations. If we're talking about fusion, then fusion has to do with the freezing and melting temperature. So if we are freezing or melting, then we would use the delta H value. Now, if we're dealing with the latent heat of vaporization, then that means we're looking at the boiling and condensation point, so we have a different delta H to use. So you have to be careful when you're looking at a problem to know which phase change is going on. If it's melting or freezing, then you'd use the delta H of fusion. If it's boiling or condensing, you'd use delta H of vaporization. Now, one important one that you do need to know is the delta H of fusion of water and the delta H of vaporization of water. So go ahead and add these to your notes. Okay, the delta H of fusion of water is equal to 334 joules per gram, and then the delta H of the delta H of vaporization of water equals 2260, so 2260 joules per gram. Now you notice that with these equations, it's a little bit simpler equation. All you have to do is take your mass, whatever the mass is, and usually it's written in grams, so your units for mass are grams, and then you just multiply it by your delta H of fusion. So delta H of fusion, for example, for water, the units were in joules per grams. So you just plug in your delta H here, and then you multiply them together. So if we're looking at the units, then remember the units for mass are grams. The units for enthalpy of fusion are joules per grams. So when you multiply these two numbers together, the grams cancel off, and we're left with joules. Okay, so that's what happens to our units. Same thing with this equation. Remember, the only difference between these two equations is that the first one is when it's freezing and melting. The second one is when it's boiling and condensing. Okay, here's question 3. When do we use the equation Q equals M delta H? Now, I'm not talking about a specific delta H of fusion or delta H of vaporization. I just want to know, in general, when do we use this equation? You have 10 seconds of think time. Go. Okay, go ahead and share with your partner. Okay, here's question 4. How do we know when to use the equation Q equals M delta H F, or mass times the enthalpy of fusion, or Q equals mass times the enthalpy of vaporization? Okay, so I'll read it one more time. How do we know when to use Q equals M delta H of fusion or Q equals M delta H of vaporization? 10 seconds of think time, go. Okay, go ahead and share with your partner. Now, before we move on to the last section, which is energy diagrams, I just want to make sure that we understand this diagram right here. Now, again, we've already looked at this, so we know that in this stage right here, because the temperature is the lowest, that is a solid. In this stage right here, it's kind of in between, so that's a liquid. And in this stage right here, it's a gas. So make sure you guys are filling this in on your notes. Now, we've already talked about these phase changes going on right now, but I just want you to recognize that this one right here, because we're going, so right here, we're going from a solid to a liquid. Remember, that's melting, or a liquid to a solid, that's freezing. So at that point, we would use the delta H of fusion. Now over here, if we go in this direction from a liquid to a gas, that is boiling. Or if we go from in this direction from a gas to a liquid, that is condensation. So at that point, we would use the delta H of vaporization. So again, you need to know when to use each one of these values. You'll be using it in the same equation. It's always Q equals M delta H if we're talking about phase changes. Okay, so if we're talking about a phase change, then this is the equation to use. But what changes, or the thing that's different between the two, is that if you're talking about going from a liquid to a gas, or a gas to a liquid, you use the delta H of vaporization. But if you're talking about going from a solid to a liquid, or a liquid to a solid, then you would use the delta H of fusion. And these values will always be given to you in the problem. You don't have to memorize any delta H's of fusion. You just need to know when to use delta H of fusion versus delta H of vaporization. Now, before we complete this last section on energy diagrams, I want everybody to stand up. We're going to do a little movement in the classroom. So go ahead, stand up, go. Okay, the last thing that we're looking at now is an energy diagram. And as it says here, an energy diagram shows how the energy is involved during a chemical reaction. Okay, and all of these parts are necessary for you to know as part of an energy diagram. Okay, the potential energy of the reactants. Remember, this is how much energy they have stored up. So not the energy of movement, but how much energy they have stored up. So in this case, we're looking at the reactants. We also need to know the potential energy of the products. And so in the phase diagrams, we'll look at these in a little bit, and we'll practice identifying these. We also need to know the activation energy. This is the energy required to start a reaction. Okay, remember last class I had a piece of magnesium ribbon. Okay, it was long like this, and if I just held a regular flame like that from a candle under here, nothing happened. It wasn't hot enough, because in order for this magnesium, which is Mg, to react with oxygen in the atmosphere, it had to have what's called activation energy. So what was necessary is that we apply enough energy to activate that reaction. So what I had to do was I got my torch out. So here's my torch. Now this has a flame that's really hot. That's really hot. So when I lit the magnesium ribbon with the torch, now I gave it enough active energy that I was able to activate the reaction. So now magnesium oxide was formed, and in the process, this actually caught fire itself, and that fire burned all the way down the magnesium ribbon until all of this magnesium was converted to magnesium oxide. Now, if you were able to look at it, the magnesium beforehand was like a silverish color, but after it all burnt up, the magnesium oxide, which was what was left here, that was more of a whitish color. So that's an example of how activation energy is required to get a reaction going. Alright, so now we're going to look at two energy diagrams, one for exothermic, one for endothermic, and you'll want to know the difference between these two diagrams, the different traits they have, and how they're different. They're very similar, but there are a few key differences as well. So first, let's talk about what's the same in each of these diagrams. Now, in both diagrams, we have potential energy on the y-axis, so potential energy is here, and then the reaction progress on the x-axis. So that's the same in both diagrams. Now, if we applied that, if we look at this right here, so actually this line right here, that line represents the potential energy of the reactants. Okay, and I'm going to do these all in different colors so you can see them. So that line represents the potential energy of the reactants. Okay, this line right here represents the potential energy of the products. So potential energy of the products. Next is the activation energy. The activation energy is right here on both of them. Now it's the energy that goes from the potential energy of the reactants, all the way to the very top of the graph. Okay, and that's what we call the activation energy. So if we go back, the green line right here on each graph represents the activation energy. Okay, I'm not going to go into too much detail on this one, but the activation complex is basically the the structure that's formed in between the reactants and the products, but I'm not going to focus too much on that. Okay, the last thing we need to identify on this graph is the change in enthalpy, or delta H. So on this graph, we're looking at these 2 points. So this is what we're going to focus on for a little bit here. And remember, this is the delta H, or the change in enthalpy of the reaction. And that's what's going to be important to determine whether or not this reaction is endothermic or exothermic. Alright, let's look at our first phase diagram. So we have it here. Here's our activation energy, and here. Now remember, this is over here is the potential energy. So at this point, here are my reactants, here are my products. Over here, we have a higher amount of energy in the reactants than the products. So if the energy in the reactants right here is higher than the energy of the products, then what has to happen to the energy? In order for the energy to drop, that means that when we go from reactants to products, energy had to have been released. It had to have been given off. If the products have less energy than the reactants, that means that energy was given off, so it was producing heat or energy. That would make this an exothermic reaction. Now, in this case, let's say here's our potential energy of the reactants, and here's our activation energy, and here are our products. Now here, reactants and products. At this point, for the reactants, the energy is very low, but in the products, the energy is very high. So what happened is that the reaction had to gain energy to go from this point to this point. So if the reactants gained energy, then that means it would look like this. Heat plus the reactant would produce the products. That makes this an endothermic reaction. Alright, now I know this is going to be more of a challenging question for you, but I know you guys can do it. And I'm going to give you guys a little bit of think time so you could really analyze these graphs, try to make sense of them. So for this question, question number 5, you are going to draw and label, without using your notes, an energy diagram for endothermic and exothermic reactions or processes. So what you'll need to do is spend about 30 seconds of think time. Okay, so you have 30 seconds to think about it. Then I'm going to let you try this on your own for about a minute, and then after that I'm going to let you guys work with your group to see who can help each other out, how you guys can help each other out, and then we'll see how you did compared to the actual phase diagrams. So you have 30 seconds to think about it. Go. Now put the notes away, and either on a blank piece of paper or scratch paper or just a small piece of paper somewhere, wherever you can find a blank spot, go ahead and draw these two energy diagrams. Alright, now we're going to do a little rapid fire, so everybody stand up and be ready to go.